Hi, Tiara. I hear you, Tiara, but I do not see you yet.
1 second,
Okay.
I think.
I got it. You got it. You got it. How you doing?
I'm fine. How are you? Oh, this is so cool.
What? What are
Oh
you
no, I
looking
didn't know I could minimize it.
at? Okay. I'm gonna try to get you on the gallery view, speaker view, whatever. Oh boy. Did you take either of your tests yet? The other tests?
Yeah, I still have one more.
All right. Which one did you take?
The chemistry one.
Was it okay?
Oh yeah,
Okay, good. What's the other one? I can't remember.
genetics.
Genetics. Oh, okay.
Yeah,
Are you more worried about that one than you were about the chemistry?
yeah.
Yeah. Yeah, because is everything on it something you've done online with the, she's doing PowerPoints and stuff, right?
Yeah, she's
Yeah.
doing like voiceovers on PowerPoints.
Okay. All right.
It's on like well, we learned 2 of the chapters in school, and then one of the chapters we learned via
Mm-hmm.
online.
Okay.
And it's
Okay.
just 2 parts to the test, so we'll see what happens.
Are you gonna have another test in there before the final?
Yeah. Well, apparently, I read her updated syllabus, and the final is optional now.
Okay.
And
Uh,
I don't even want the grade for this class to show. So I don't.
you don't? You do or you don't?
I do not.
Okay. All right. On genetics, you mean?
Yeah,
Okay.
I
All
really
right.
don't. I mean, I'm still trying, but
Yeah.
just
All right.
I have a question.
Yes, ma'am.
Why do I always have to put in a password?
Oh yeah, I
Because
have to do that too.
well, yeah, I'm gonna try. I keep trying to do this. I'm gonna try to redo all these meetings so the password's automatically in there. But you guys all have it, so that's that extra layer of security that Zoom put on it. Yeah, that and the waiting room are the 2 things they are trying to use to keep people from interrupting people's meetings with weirdness. Okay, so yeah.
I was just confused because I was like, I always forget I have to put a pin in, so that's why I'm always like a couple seconds late.
That's okay. I'm gonna try. I got a lot to do this weekend. I have not graded your test yet, but I will. You're next up. I was doing homework. So I'm gonna do that this weekend. I'm gonna try to make some assignment sheets this weekend. This is might be the least fun Easter I've ever had. But anyway, whatever. We'll see. We'll take it as it comes. So everybody doing okay?
Yeah.
Alexis, did you have a test? You had tests too, didn't you? That coming up like this week?
No, the last test I had, like, it was like I had the solutions test and then I had your test, but that was in the same week last week.
Okay.
This week is just quizzes.
Okay. Deborah, did you have another test?
I have one last week.
Yeah, I have another test. Oh,
yeah.
Next week.
Mm-hmm. Okay. So Deborah, what did you say?
I had a bio test last week.
Did that go okay?
I don't know. I don't know what I got.
Did it graded yet? Okay. That's the big sticking point, man. I thought I had it made when I had a way to deliver my lectures, and then all of a sudden I thought, ooh, that's not quite enough. So, but I will try to have you guys. I think I'll have your tests done tonight, and as soon as I grade them, I send them off. So, so you should get it tonight or tomorrow. Okay. What are you up to? You got any? You had any tests lately, other than the math? Okay. All right. You're the lucky one then. Okay. All right. So, guys, let me go ahead and share the screen, and we'll start talking about whatever you need to talk about, and maybe talk about something new. Let's see. I should start in a few seconds. Please, I'm already started. No, I don't want any new tips. I want to start. Okay. I'm going to resume my share. Okay, I'm having trouble getting it to share. I'm going to wait for a minute. You know what's doing this crap? Okay, let's do it later. All right, there we go.
I have a question.
Yeah.
So the stuff we've been doing so far is not too bad.
Yeah.
Is it gonna get worse? I feel like this stuff is just a little too easy right now.
Well, you know what? The chapter we're getting ready to do is not that easy. Okay, it might be on the level with some of the integrals, although we'll be able to do it. It's not an issue, I don't think. But it's called sequences and series, and you may have to do a little more work on it in terms of it being new stuff. You know what an integral was. I was just showing you how to do lots of different kinds of integrals. You don't know what a sequence and a series is at this point, so it's brand new stuff. We're gonna just do that. Now that quiz you got one quiz left that's on Moodle right now, and it's the one on improper integrals. So that's not due until Monday, guys. Let's just have it due Monday by class time. Okay, so you should have plenty of time to look at that one. And I don't think that's just the stuff I've been doing for the last couple of days. So did anybody have any questions on that stuff, on the improper integral stuff? All right, I'll let you work on that over the weekend, and that quiz will be due Monday. If any questions come up while you're doing the homework or whatever, just shoot me an email this weekend and we'll set something up. You know, we can do it afternoon, night, whatever, if you got any particular questions you want to ask. So what we're doing now really doesn't bear much resemblance to integrals. It does have some things to do with limits. And I've got to introduce some new topics, new words. So let's start to do that today, see how far we get, and then we'll continue it on Monday since we have tomorrow off and we have a big Easter break. So first definition this is section 11.1. And oh, by the way, your homework on this, it's on this sheet that we're recording, but I also put it on Moodle as a single assignment. I have not had enough time in the last couple of days to make a full-blown assignment sheet. So as a matter of fact, I'm thinking about doing it a day at a time, because in a lot of the, not so much with you guys, but with other classes, I'm kind of dragging, and the assignment sheet doesn't work very well, at least if it's more than 5 or 6 days. But anyway, I'll let you know how that's going to play out. But right now, your assignment in this section that I'm doing right now is on Moodle, and it will say 11.1 sequences, and that's your home. That'll be the homework. It's the beginning of chapter 11 in the first section. Okay. Let's talk about what a sequence is. I think you guys probably have a general idea of what a sequence is. And in this particular application, we were talking about sequences of numbers. And those sequences of numbers are going to be sort of generated by these functions, or these terms that we have. So let's just read the definition, and I'll give you some examples. It says a sequence is a collection of real numbers that is in a one-to-one correspondence with the positive integers, or you can think of it as a function whose domain is the set of positive integers. So I'm going to denote sequence elements like this, A1, A2, A3, A4, and literally it'll just be a sequence of numbers. I might, for example, say, here's a sequence of numbers, 1, 3, 6, 8, whatever, okay? But ultimately what we end up with here is a function that generates those numbers. And in these sequences, we're only going to plug in positive integers. So we're going to only plug in 1, 2, 3, 4, so that we're going to get these sort of isolated values of the function. So A1 is f of 1, A2 is f of 2, and so on and so forth. AK is going to be f of k, whatever that is. And we call each one of these things terms of the sequence. And we call that the kth term. That just means one down the road there, the kth term, okay? So what we do to look at these things is the following. We define this function. It looks like this, and it looks like a typical function. And the function's on the inside there. It's sort of like f of n is going to be equal to minus 1 to the nth power. Okay, so that's what the function looks like. And we put an n there instead of x there, guys, and later on you'll see that when we put an x there, that just means all real numbers, basically. But for these sequences, we're only going to plug in positive integers. So for example, if I wanted to find out what a1 was, I would just plug 1 into this function. And a1 is just f of 1. And we usually just refer to it as a1. And if I plug in 1 to this, I get minus 1 to the first power, which would just be minus 1. So what we say is that the first term of this sequence is a1 equal minus 1, okay? I don't have to go through all this functional notation every time. A2 just means you're going to plug 2 into this. So if you plug 2 into this for n, minus 1 squared is going to give you 1. So that's the second term of the sequence. So A2 is just that thing. That's called right there. That's called your A sub n. It's whatever you get when you plug in whatever the n is right here. 1, 2, 3, whatever. Okay. So if I plug in 3, it would be minus 1 cubed, which is just minus 1, and so on and so forth. Hey, what would A4 be, guys? Tell me what A4 would be.
1.
It's 1, because I've got minus 1 to the fourth power. It's going to be 1. And pretty quickly you see that this thing just bounces around, because all that's going to happen when you raise it to this power is if it's an even power, you're going to get 1, because you squaring or fourthing or whatever. If it's an odd power, you're going to get minus 1. So if I also think about how to look at this on a graph, it's a little bit different from what you expect. Whoops, let me move down a little bit. It says when I plug in 1 right here, I get minus 1. So it's actually just a point on the graph. And since I'm only plugging in integers, I plug in 2, I got 1. I plugged in 3, I got minus 1. I plugged in 4, I got 1. And what you can see is it's just going to keep bouncing up and down between 1 and minus 1. And that's the picture of the points in this sequence, or the numbers in this sequence, okay? So we don't connect the points, because the points, we're just evaluating this thing at integers. So 1, 2, 3, 4, whatever, 5, and so on, okay? So it's kind of a stripped down function that you only plug in whole positive numbers, whole positive integers. Well, positive integers, that's what a positive integer, guys, is just defined to be 1, 2, 3, and so on, just those numbers, okay? Okay, so so that's what we mean by these things. Let's do another one. If I have this one right here, that the nth term, that's the way these things sort of come, guys, is that they'll come with a set of brackets with an an in the middle. And the an is the thing you're plugging the n into. That's your function. So my a1 would be 1 over 1 plus 2, 1 over 1 plus 1, which would be a half. If I plug in 2, it'll be 2 over 2 plus 1, which will be 2/3. If I plug in 3, it'll be 3/4. If I plug in 4, I'm going to do one more. What will it be if I plug in 4 here? What will that be, guys?
4/5.
Yep, 4/5. Yep, so that's not so bad. And then it said, I think the example in the book said, find the 10th term. Well, that means you're going to plug in 10. So it'll be just 10 over 11. Now, if you look at these for a minute, and this is going to have something to do with what I say in a few minutes. 1/2 is 0.5. 2/3 is 0.6 repeating. 3/4 is 0.75. 4/5 is 0.8. If I go all the way out to 10 over 11, who's got a calculator with me? Anybody got a calculator by your side?
Yeah.
Okay, find out what 10 over 11 is. Give me a decimal form for 10 over 11.
0.9090.
Put 20, what is it, 0.29?
No, 0.9090.
Oh, good, 0.9090, that, okay? Okay, so guys, if you look at these things, I'm gonna sort of give you a preview of what I'm gonna do with these things. What we're interested in is do these terms of this sequence approach any particular number? So if you look at what their decimal values were, we got 0.5, 0.66, basically, 0.75, 0.8, and when we went all the way down to 10, we got 0.9. Does it look like these numbers are approaching any particular value here, guys?
1.
Yeah, it does look like it's approaching 1. And I bet if we went way out in the sequence and did maybe 100 over 101, so that would be the 100th term, then we'd come up with something that was even closer to 1. So looks like you had the calculator, Alexis. Put 100 over 101 in.
It's 0.9900.
Okay, 0.9900. It's getting closer and closer to 1. And the further I go out in this sequence, the closer to 1 it gets. We're going to say that the limit of that thing is 1. So we're going to continue to talk about limits. Okay. All right, let's do a couple more examples of sequences though. Here's an AN right here. And it says find some of the terms in the sequence. So I start by plugging in 1. So 2 plus 0.1 to the first is 2.1. If I plug in 2, in other words, if I square 0.1, I'll get 0.01, so 2.01. If I plug in 3, I'll get 0.001, so I get 2.001 there. And you can kind of feel like right now, this one is doing what? This one is getting closer and closer to what here, guys? 2. Yeah, it looks like it's getting closer and closer to 2. So that's sort of what we're after, to see if these things are getting closer and closer to anything. Okay, the next one. These are kinds you see quite a bit. They're terms of a sequence, and the sequence is defined by -1 to the n plus 1 over n squared, or times n squared over n plus 1. And it doesn't look any different from the ones we just did, except this -1 to the n plus 1. Now, if I keep plugging things into n here, I'll either get an even number or an odd number. I'll get an even number when this whole power right here is even. I'm sorry, I'll get a 1. And then if it's odd, I'll get a -1. Okay, so for example, if I let n be 1, it'll be -1 squared over 1 squared over 1 plus 1, which is 1/2. So that -1 squared will give me positive, so that'll be 1/2. If I let n be 2, I'll get -1 cubed, which is -1, 2 squared over 2 plus 1 here will be 4/3. That one will be negative. If I go to the next one, if I go to A3, what I wind up with is -1 to the 4th. Clearly that's going to be positive. And I'll end up with 9/4. What's going to happen with these terms, guys? I mean, what can you say about the next one?
It's going to be odd. I mean, not odd, negative.
Yeah, the power is going to be odd, so the next one's going to be negative. So what we've got here is what we're going to, in the end, call something, we say it's alternating, okay? And when you see something like this right here, that's what you're looking at. You're looking at something that keeps changing the sign because it's just powers of 1, okay? It is also possible to have a sequence that just has the same thing over and over again. So for instance, my function associated with this thing might be f of n equal 4. And so in other words, that's my an. So my an in this case is 4. And it doesn't really matter what I let n be. No matter what I let n be, if the function is 4, what's going to come out of the function is 4. It's the constant function, okay? So f of 1 is 4, f of 2 is 4. So a1 is 4, a2 is 4, a3 is 4. So we've got that. Now, if I said to you, do you think the limit, is this approaching anything? 4, 4, 4, 4. I mean, not only is it approaching something, it actually is something all the time. And what is that? 4. Yeah, so we would say the limit of that sequence is 4. Okay, so we're using some of the same ideas about limits that we have had before. That they're, you know, the limit of a constant is a constant, and so on and so forth. Okay, now there's another way to define sequences, and it's called a recursive sequence. And I want to talk to you about recursive sequences and tell you how to generate recursive sequences. Instead of giving you a formula for the sequence, what a recursive sequence does is it tells you where to start with a sequence, and then it tells you what the next term is going to be. Now that's a little bit strange, but I bet all of you have, there's a really famous sequence I bet all of you have seen. I'm going to talk about it in just a second. Let me show you what it means here. Suppose we had this, and suppose you started off the problem and you had this right here, all of this. And they tell you that you're going to start with A1 being 3. Okay, let me move it up a little bit. You're going to start with A1 being 3. And your rule says AK plus 1 is twice AK. Now, what that means is the one right after K is twice, or the one right after AK is twice the one before it. See, K plus 1 would be right after K. So here's what we do. We start, and let me get rid of this because I didn't want the whole thing there. Okay, what we start by doing is we start at A1 equal 3. And then we use this rule. And we say, okay, on this one right here, I'm going to let K be 1. Because if I let K be 1, I'll have A2. Because 1 plus 1 is 2. And then that your rule says that A2 is twice A1. Right? K is, so K is 1 here. Okay? And because K is 1 and this is 1 more, that generates A2. So I end up with A2 is 2A1, and they gave us the place to start. They told us A1 was 3. So the answer is 2 times 3 or 6. I should have written that there. It's 2 times 3. Okay, now let's pick up with the next one. Let K be 2. Look at the formula. If K is 2, then we're finding A3. And the formula says it's twice 2 times A2. So A3 is twice the one right before it. And the one right before it was 6. So it's picking up the one right before it every time. Now, it doesn't have to be immediately before it. You might have a gap of 2 things here, but we'll talk about that later. Let's do one more. If K is 3, then you'll have A4, and that'll be twice A3. So A3 was 12. You go back to the one right before it. So twice 12 will be 24. So the things in this sequence so far are 3, 6, 12, and 24. Now, what I want you to do right now is tell me, let's see, did I do it down here? Yeah, I want you to tell me what if K is 4. Let's do this here. I'm running a little bit out of space there. But if K is 4, then that would be 4 plus 1. What would A5 be? Play it all out. Don't tell me the steps. I want to know what the number is going to be.
48.
Say it again, Alexis.
48.
Yeah, because remember what happened? A5 turned out to be 2. The one right before it, A4. All right, that's A4. And A4 was 24, so that's 2 times 40. Sorry, that's 48. 2 times 24 is 48. Let me get rid of that. Do That's 2 times the one right before it, which is 48. Okay. So in other words, they tell us where to start and they tell us how to get the next one. That's called recursive. Recursive means to do something over and over and over again. And that's what we're doing here to generate the elements here of this sequence. All right, let me show you another one. Anybody question about that?
I think my sister was doing something like this in school.
She might have been, what grade is she in, Alexis?
She's a senior, but she's in advanced functions and modeling.
Okay, that'd be where this was, okay? It's called a sequence, and it's a recursive sequence, okay? Has anybody ever done this before? Did you do it in school, Alexis?
I remember some of it, but I hated this stuff.
Okay.
But I remember I did good in that class, but it wasn't, I don't know. I can't right now.
Well, it's
I remember it was high school.
it was high school, right? We'll make it more fun in college, okay? Anybody else ever seen this? Recursive sequences? I bet I'm gonna give you something now that you might have seen. And it turns out to be a recursive sequence, but in high school, a lot of times they won't tell you anything about it. But let's look at this one. So I want you to look at this sequence down here. This one, I did really lousy screenshots on this. But here's a sequence. A lot of times we're given a sequence and we're sort of asked to figure out how we get the next term. So in other words, if you can see a pattern. So here I've got 1, I'm starting with 1. The next one is 1. Next one's 2. Next one's 3. Next one's 5. Next one's 8. Can you tell me what you think that is? Anybody got a guess about what that one might be? Yeah, Dion, what you got?
13.
Yeah, actually, Dion's right. It's 13. Dion, tell us what you're seeing.
Oh, I already know it. But you add the number, like the number before it with the number.
Yeah.
There.
So for instance, 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 13. The next one's going to be what?
21.
21. So I'm adding the previous 2 to get the next one. So now it depends. You see what I did, Alexis?
Yeah, I see it now.
Okay, good. So tell me Alexis, you tell me what the next one is.
34.
Yes, it's 34. Okay. Does anybody know what the name of this sequence is? Anybody know? It has a very famous. Say it again.
Alpha.
No.
It's the Fibonacci sequence.
It's okay. Dion knows more about this than anybody apparently. Okay, so guys, this is called the Fibonacci sequence. Okay, let me write it down. So Fibonacci sequence.
Is that a person?
That's a person. I'm gonna tell you about him right now. Early 1200s, known as the greatest mathematician of the Middle Ages. That's a long time ago. Okay. Fibonacci means son of Fibo or Nachi or something. I don't know, whatever. It's Italian. He was Italian. And he's actually famous for not only this sequence, but more famous in a way for introducing to us the numbers we use to count with, what we call the Hindu Arabic numerals. What you look at is a number 1, 2, 3, 4. Now, if I told you right now that we were going to start working with these numerals, 1, 5. What kind of numerals are those, guys? You know what those are? They're Roman numerals, aren't they? This is 1. That's 5. That's 10. That's 50. C is 100. That makes sense. C is a Latin word group, guys. Century, 100, but C stands for 100. So this was a kind of a messy way that the Romans, for one, used to do counting and numbers and so forth. So for instance, if I said IX, do you know what IX is?
9.
It's 9. It's basically take the 10 and take 1 away from it. Whereas XII would be what?
12.
It would be 12. Now, these were hard to use. The thing that makes your number system superior to this is that when you look at 228, you're not just switching numbers back and forth randomly, like IX and XI. XI would mean 11, whereas IX means 9. You've got, these are placeholders for instance, hundreds, tens, and ones. These kind of numerals were called Hindu-Arabic numerals because in India and the Arabic world, they came up with these kind of numbers. They are easier to add, they are easier to multiply than Roman numerals were. Now, how does this connect to Fibonacci? In the 1200s, Italy was still using Roman numerals. Fibonacci's father was a merchant, and he traveled with his father, and he had to keep books for what they had sold and what they had bought and so forth. And what they discovered in their travels was that these Hindu-Arabic numerals were a lot easier to keep your books with than these long, messy Roman numerals. You know where the only place you hardly ever see a Roman numeral anymore? The place you really see it is if you look at the end of a movie, it'll give you the year the movie was made in Roman numerals. Has anybody ever noticed that? If you look at it real quick, you'll have to like hit pause because they get so long and messy that you can't read them quickly. Okay, so Fibonacci proposed, sort of dropped the bomb in Italy and said, you know what, I'm not using these Roman numerals anymore. And people started using Hindu-Arabic numerals. And there was a time when this is ironic because society always sort of resists new things. Even into the 1200s, the police in Italy were throwing people into jail for using Hindu-Arabic numerals instead of using Roman numerals. They're like, no, this is the way we've always done it. We're going to do it that way, or we're going to throw you in jail unless you count with these all you want. Okay?
He went to jail?
He didn't go to jail, but his people who started using these things were in danger of being locked up for using these instead of these. Okay?
You deserve to go to jail too, then. That's not fair.
But no, he deserves to get a lot of credit because what he did was a good thing. It's much
That's
easier.
true, but like, how he ain't gonna do jail? That's crazy.
Well, a lot of times the person that invented something or introduced something is gone by the time people start using it. So.
Oh, he was dead.
Yeah, probably. Okay, so here's what I want to show you. That's Fibonacci was a interesting and famous guy. But let me show you how this one works. Let me show you how it's a recursive sequence. Let me get rid of some of this stuff. That's what I do when I teach math history, guys. We talk about what happened. How did we get to where we got today? Some people mistakenly think that math has always been like it always is and will be and so forth. It's not true. It's evolved. Okay. So here's how we do this as a recursive sequence. We say that we're going to start with two pieces. We're going to start with A1 is 1 and A2 is 1. And it says that we're going to generate AK plus 1 by the 2 before it. And notice, guys, K and K minus 1 are the 2 before it. So, for example, if I said, let's let K, we already have A1 and A2. Let's let K equal 2. So I'm finding A2 plus 1 right here. I just plugged it in right there. So that's A3 plus, A3 equal AK, which is A2 plus K minus 1, and K was 2, so I get, sorry, that's a 1. Let me start this over again. I sort of got messed up. K is 2. 2 plus 1 is 3. So I'll get A2 plus AK minus 1. Well, 2 minus 1 is A1. So basically, that's a way to say that the third one is the sum of the 2 right before it. And that's exactly what we saw in the Fibonacci sequence. If I went a little further and I said, okay, I want to let K be 3. let K be 3. Then A3 plus 1 means A4 is equal to, if it's 3 right here, it'll be A3, because that's K. And 3 minus 1 is 2, so A2. So what we get is that. Now in this case, A3, A1 and A2 were 1 and 1. Okay, so we got, for the next one, we got 2. In this one, A3, we already found was 2. From this one, and this was A3, was 2. And A1, or A2 was 1. So that's how we got the next one. We got 3. So we continue to keep going, feeding into this, what we got before, okay? That's called the Fibonacci series, okay? Sequence, okay? Okay, so let's look at another one, or another thing. Now, what I want you to look at this point is a sequence that says 2 plus minus 1 to the nth. And I'm gonna generate a few of these pieces here. I'm gonna let n be 1, and because it's 1, that's gonna be negative 1/2, so 2 minus 1/2 will be 1.5. If I go down to the second one, minus 1/2 squared will be 1/4, so that'll be 2 plus 1/4, or 2.25. If I let n be 3, I get 2 minus 1/8, and there's a reason why I'm putting the decimal points here, guys. That'll be 1.875. If I look at A4, that'll be 1/16, so that's 2 plus 1/16, and that's 2.0625. Now, if I look at this thing in the following way, let's plot these things. Let's kind of plot these points. It looks like we went from 1.5 to 2.5 to 1.8 to 2.0. It looks like we're bouncing around 2. So I'm going to draw I'm going to draw that line at 2. If I look at what A1 is, I plotted this, it's 1.5. If I look what A2 is, it's 2.25. So that thing right there is A2. This is A1. If I look at A3, it bounced back down below, right there. And if I look at A4, it's 2.065. But what you see is it's bouncing around, but as it bounces, it looks like it's getting closer and closer to something, okay? So what does it look like it's getting closer and closer to, guys? Well, yeah, it was further, it was half a unit away from 2 down below, and then it was only a quarter of a way below. Here it was about, 0.13. It looks like it's bouncing around, and it's bouncing around because of that negative to a power there, guys. It's bouncing around, but in the end, it's getting closer and closer to 2. So, and actually I did one more, that A5 down here was 1.9675. So it was really, really close, but right under 2. A6 was like 2.01. So it bounced right above. I ran out of room here for what I wanted to do, but you see it's getting closer and closer to 2. What we say is it's kind of closing in on 2. It closes to 2, all right? I should have put closes in there. That's what I meant, really. It closes in on 2, which means that sequence also has a limit. What we mean is that we can get closer and closer to something the further we go down with plugging these numbers in. All right. So the limit is what it's getting closer and closer to, just like it is in everything else we've done. And that's the way we write it. We write it as the limit as n approaches infinity. And remember, n is still just 1, 2, 3, 4, 5. It's not all numbers, it's just the positive integers. But it's going to 2. So the bottom line is we can make the terms of this thing as close to 2 as we want, and we call that arbitrarily close, if we go far enough out in the sequence. We want to get really, 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 really close to 2. We'll let n be 100 because it's going to get tight on 2. It's going to get really tight on 2. Now, so we say that 2 is the limit of the sequence. Okay, 2 is the limit of the sequence. Now, so what we're looking at here, guys, is this, and this. Now I'm going to get a little bit of terminology in here. If this is AN, that's the sequence, and we take away 2, all right, then what it says is that this thing can be made arbitrarily. Let me mark that out. All right, this thing, the 2's go, all right, and then we'll get this 1/2. If I look at it, 1/2 to the nth power, and whether it's minus or plus, that'll be getting closer and closer to 0, and I will end up with a limit of 2. Okay. Now let me show you the actual definition. Okay. Here's the definition will make probably better sense without my example up there. All right. It says the sequence AN has a limit L, or we say converges to L, denoted by the limit as n goes to infinity of AN equal L. If it doesn't have a limit, we may say it just goes to infinity, but because there are some things that go to infinity. But we say AN goes to L as n goes to infinity. Now, this is fancy notation here, guys, but let me see if I can describe to you what it says. AN is your sequence. If L is the limit, then the difference between your terms and the limit is less than what we call epsilon here. Now, epsilon is a Greek letter.
How you draw that?
What's that?
How you draw that?
It's like you do this, you kind of do that, and you put a mark in the middle.
Oh, okay.
Okay, it's a Greek letter, okay? And what it says is that I can make this less than epsilon whenever n is greater than capital N. Now, epsilon is a small number, and then I'm going to write no matter how small epsilon is. No matter how small epsilon is. So ultimately what it says is that you can get as close as you want to 2. So let's say, for instance, that we had this sequence again, all right? And say I wanted this number right here to be very small. I wanted that thing to be very small. And suppose I said I wanted it to be this thing. I wanted the number that I'm getting out of this sequence to be within 1,000th. Was it within 1,000th of 2? So for instance, if I plug 7 into this part right here, then 1/2 to the 7th is 0.007. So I have gotten within 0.007 of 2 there. That's not close enough. If I let n be 8, I've gotten within 0.003. That's 3,000ths. Not close enough. I said 1,000th. I wanted to get within 1,000th. But it is getting smaller, guys. I'm getting closer to 2 because this 1/2 to the nth thing is getting closer and closer to 0. So if I let n be 9, 1/2 to the 9th, and I'm letting n be 9, is 0.00019. I have now gotten far enough out so that I am within 1,000th of 2. Okay? And what I'm saying is this: even if you pick epsilon, this number, if you pick this epsilon to be within 1,000,000th, you pick epsilon to be really small, it says you can make the sequence differ from the limit if you let n get big enough. Now, if I wanted to be within 1,000,000th, I might have to go out further, okay? But I can do it, all right? That's what it means for a limit to exist. That's a technical definition for limit of a sequence. Now, let me say one other thing. There's another part to this definition. How far did it take us to get to within 1,000th, guys? How many terms did we have to go?
9.
We had to go 9. It was not good enough to be 8. But since we're only plugging in integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, anything anything more than 8 is going to get it, because 10 will definitely be that close, 11. So that's what this last piece says. It says you can get as close as you want to the limit that you say is 2, all right, whenever little n is bigger than some capital N. Well, the capital N that it always has to be bigger than here is 8. And so what that says is if n is bigger than 8, then we are going to be within 1,000th. That's all it's saying. So if a millionth was, if I tried to make it as close as a millionth, that I had to go out to 20, then the n, when 20 did it, then the n that I would need would be anything bigger than 19, or all n's bigger than 19, because it got there at 20. Okay. All right. So let me show you. I sort of talked through it there, but I wrote it here. I said, so whenever n is greater than 9, this thing is less than 1 over 1,000. Okay, the difference between that sequence, which was like 2 plus minus 1/2 to the nth minus 2. The difference there, I could get that close, and I can get as close as I want, no matter how you do that. So that's what that technical definition means. We'll come back to that and look at it again.
The answer, like,
the answer, well, I'm just describing to you the definition. It just says you can get as close to 2 as you want, no matter how small we make how close you want it. Guys, look at absolute value. Absolute value means the distance between the sequence and the limit here. This is 2. That's what absolute value means. If I ask you to find the absolute value of minus 3, it's the same thing as the absolute value of 3, which is 3, and that's just indicating its distance from 0. Absolute value is always distance. The absolute value, a minus b, is the distance between a and b. So this is saying the distance between what we compute the sequence to be and 2 can be made smaller and smaller and smaller, right? Which means this thing is, the limit is 2. We're approaching 2. Epsilon is how small you want to make it. And epsilon can be whatever you want to make it. What's that?
Like -1/2 z.
This is n. I'm sorry, guys. That doesn't look good. It's an n. It's the original sequence we were looking at.
Oh, okay.
Okay, sorry. That's the n. This is the an we were using. This is the an we were using. And we're saying if we can make the difference between that, if n is big enough, then its limit exists.
And that's a 2, like minus.
And that's a 2. And that's what the limit is. That's a 2. Okay? All right, now, suppose I gave you this one. Look at this one right here. If I said, let's look at the sequence 2 to the nth. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. What's 2 to the fifth? 32. We're just doubling it here, guys. 32, 64. Let me ask you this. Do you think that sequence right there has a limit?
No.
No, I don't think it has a limit. If I let n get bigger and bigger, what's happening to the number? It's getting bigger and bigger, isn't it? Here's the definition, the technical definition for that. It says the notation, limit of an as n goes to infinity, equal infinity, means that for every positive number p, there is a number n such that an is bigger than that p. So if I said to you, oh, I don't think this thing is going to infinity. I think it's going to stop at 3,438,000. What this says is you can find an n that, nope, that's bigger than that p you had, okay? So you can always exceed that real number no matter what it is. You can always exceed p, okay? So that's what I said down here. Pick a number n as large as you want. We can find a term 2 that is bigger than that number. So if you pick a number 10,000, that's what I did here, guys. Look at what I did. I said, suppose I say p is 10,000. If I can find a number bigger than 10,000 in this sequence, then I've said, oh, well, I can find any number bigger. So I took powers of 2, 2 squared, 2 cubed, 2 to the 10th I tried. That wasn't big enough. Not as big as 10,000. 2 to the 13th, I thought that would get it. Didn't get it, okay? It was 8,192, but when I got to 2 to the 14th, I exceeded 10,000. So for every number, for every n bigger than 13, for every n bigger than 13, what happens here is that's your capital N. You exceeded something. And if you can keep exceeding that, it doesn't have a limit. And what we say is that it goes to infinity. You can kind of see that, but that's the technical definition. And we can say that AN increases without bound. AN increases without bound. Okay, let me give you a real important theorem that's going to help you do some of your homework. Only part of your homework, though. We're going to continue this on Monday. It says, let AN be a sequence, and suppose f of x exists for every real number. In other words, we've got a sequence, and then we got a function that looks like that with an x in it instead of an n. This is powerful for us because we know how to find a lot of limits. We just finished a whole chapter on limits, that L'Hopital's rule and stuff. It says, if the limit of just a regular function, the kind we've been dealing with f of x is L, as x goes to infinity, then the limit as n goes to infinity is also L. So if I looked at, and if it goes to infinity, the sequence will go to infinity. So if I looked at this sequence right here, guys, AN is 1 plus 1 over n. So the function that applies to that is f of x, or that corresponds to that, is f of x equal 1 plus 1 over x. I bet you guys can tell me what the limit of that is. I mean, the limit as x goes to infinity of that, that's going to go off to 0. That's going to be 1. What it says is if the limit of that looks like is 1, then the limit of the sequence will be 1. So all you have to do to find out whether a sequence has a limit or not is take the limit as you normally would with x going to infinity. Now, part of the difference is, and we'll look at this again more later, but when you're looking at f of x equal 1 over x, this is the whole line here. When we're looking at f of n, or the sequence 1 plus 1 over n, it's just a bunch of dots. We're not going to play connect the dots in this because it's only defined for plugging in integers like 1 and 2 and 3 and 4, whereas this one is defined for all the values along the line there. All right, let me try one more here. Let's find a good one. I don't like that. Couple of things. Yeah, this one's easy. Got a couple of easy ones here. So I'm looking to see if this sequence has a limit. It says you can look at the limit of that function. Notice if x squared, if you're going to infinity and you're squaring x and you're not doing anything but taking away 1, this thing's getting bigger and bigger. So that says the limit of this sequence is infinity. If you plotted some of those points, you'd see that they just keep going up and up here. Okay. The next one, if you look at the next one's kind of interesting. This is just 1s and minus 1s bouncing back and forth like we saw to begin with. Does that ever approach a particular number? If I'm bouncing back and forth, can we say that has a limit? Now, we talked a little bit about this in Calc 1, but maybe not a lot. It oscillates. It's not getting closer and closer to anything. If I say, oh, it's getting closer and closer to 1, it soon jumps to minus 1. And then it jumps back to 1, down to minus 1. So this limit does not exist. That's another way that a limit might not exist. So it can be going to infinity or it can be bouncing around. Now here's where, guys, what you just did comes into play. What if I know if that one is approaching something? By the way, if the limit doesn't exist, we say it diverges. If I want to look at this, I'm going to take a look at the limit as x goes to infinity of a function whose domain is real values. I think you guys learned how to do that in Calc 1. You remember what we did in Calc 1?
Leading coefficients.
Oh.
Yeah, we looked at the leading coefficients. It was 2/5. But you know something? We have something more sophisticated now. If you want to, you can use L'Hopital's rule on it. So take x going to infinity, because that's an infinity over infinity form. That'll be 4x over 10x the x's cancel out, and we'll get the 2/5. So you can use L'Hopital's rule on these things to find out if they converge or diverge. This one, L'Hopital's rule. You want to know if it converges or diverges? Limit as x goes to infinity of 5x over e to the 2x. You guys can see that that's infinity over infinity. Use L'Hopital's rule. And L'Hopital's rule says this is going to be 5 over 2e to the 2x. And where do you think that one goes, guys?
0.
Numerator's stuck, denominator's getting bigger and bigger. Where's it going? You heard it. It's going to 0. Okay? So what happens here is that the bottom is growing faster than the top, guys. The bottom's growing faster than the top. Now, I am kind of stuck in the middle of something here. I am going to shave your homework down. So, and I'm going to send you an email of the ones I want you to do, not the ones that are on the sheet on Moodle, because that's the whole section, and I have not finished the whole section. I'm going to you can do all the ones from, if you want to get started, you can do all the ones in the following. Let's go down here.
That's the mama. Tell your mama I like her hair.
Whoa. So what I'm going to do is shave your homework down, okay, guys? So I will send you an email to that effect, and you won't have a whole lot of homework to do this weekend. You'll just be looking at some of these things, the first part of it, okay? All right, anybody, I'm stuck in the middle of something here. Anybody any questions on this?
Yeah, like, what's this used for?
Alexis always asks me the same question. I always have to be. Sequences and series are used. If I said to you, if you were stuck on a desert island, and this isn't a very good example, but I'm going to give it anyway, and you wanted to find out what the value, for some reason you were working on something, and you needed to know what f of 0.23 was. You're stuck on a desert island, that's 0.23, and you don't have your calculator. This is kind of a weird example, guys, but I'm going to say it right now. Could you tell me what that's equal to?
No.
No. There is a way to use series to write things as a polynomial function without the e. And polynomial functions are easy to evaluate. You just plug in 0.23 and you raise it to powers. If you got plenty of time on a desert island, you can raise things to powers all day long in the sand, on the beach, whatever. We will get to this. We will talk about why it's important, but one reason it's important is because we can rewrite functions using sequences and series. Okay, again, I'll shoot you a quick email to the ones I think you can do, and just ignore what's on that Moodle assignment, and we'll pick it up on Monday, okay? All right. Everybody have a nice Easter, and I'll try to get your test back tonight or tomorrow, and I will see you on Monday. All right. Bye-bye.
Yes.